Here's the same technique applied to a 560 ohm resistor. Let's again employ a 5 ohm sensing resistor. The source voltage waveform displayed on channel 1 shows it to have the following properties. Note channel 1's vertical sensitivity is set to 2 volts per division, and the horizontal sensitivity is set to 2.5 milliseconds per division. It looks like the source has a peak-to-peak span of, let's say, 7 divisions. Again, you'll note it's a little asymmetric and that the positive half seems to be larger than the negative half, but not by much. Regardless, at 2 volts per division, this corresponds to a peak-to-peak value of 14 volts. If we assume this waveform to be zero-centered, which it obviously isn't, a 14-volt peak-to-peak value would correspond to a peak value of 7 volts. A 7-volt peak value would correspond to an effective value of approximately 4.9 volts. Looks like the supply voltage has a frequency of 79.9 Hz, almost 80 Hz. Assuming the source voltage is our reference, given the above data, it can be said that the phasor representation of voltage across the resistor is 4.9 volts at an angle of 0 degrees. Ohm's law shows us that the current drawn by the 560 ohm resistor should be roughly 8.8 milliamperes at an angle of 0 degrees. Let's see if this is the case. When we display channel 2 adjusted to compensate for a 5 ohm sensing resistor using a 200 milliamperes per volt transfer function, we are rewarded with the following display. Note channel 2's vertical sensitivity is set to 4 milliamperes per division, and the horizontal sensitivity for both channels is still set to 2.5 milliseconds per division. The two waveforms are obviously in phase with one another in that the direct means of measuring and displaying voltage across the resistor, channel 1, simultaneously peaks and valleys with the indirect means of measuring and displaying current through the resistor, channel 2, indicating that our resistor is obviously wholly resistive in nature. This is the larger take-home point. There exists no relative phase shift between the voltage and current for this resistive element. This being said, we can still make magnitude measurements of the current waveform with the understanding that there might be some inherent inaccuracies. It looks like the indirectly measured current waveform has a peak-to-peak span of, let's say, 6.2 divisions. You note it's a little asymmetric and that the positive half seems to be larger than the negative half, but not by much. Regardless, at 2 volts per division, this corresponds to a peak-to-peak value of 24.8 milliamperes. Again, note, because we're using the automated transfer function, channel 2 is measuring current. If we assume this waveform to be zero-centered, which it obviously isn't, a 24.8 milliampere peak-to-peak value corresponds to a peak value of 12.4 milliamperes. A 12.4 milliampere peak value corresponds to an effective value of approximately 8.8 milliamperes. Given there is no phase shift between voltage and current, it can be said that the phasor representation of our current through the resistor is 8.8 milliamperes at an angle of 0 degrees, exactly in agreement with our previous calculations. That is impressive. Only very rarely does it work out this well. I think I'm going to take the rest of this lecture off and let you do the work from here on. Let's make this an exercise that necessitates active involvement on your part in the form of a mystery. Let's say we set up a 5 ohm sensing resistor in series with a mystery element in the following fashion. Channel 1 is measuring the voltage across the entire series circuit. Channel 2 is measuring the voltage drop only across the sensing resistor. Let's say we're safe in assuming that the inclusion of the sensing resistor in series doesn't adversely influence the total impedance of our larger mystery element, now that the small voltage drop across the small sensing resistor is also negligible in comparison to the supply voltage. If we show channel 1 the source voltage on the oscilloscope using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 100 microseconds per division, we are rewarded with the following display. See if you can determine the peak-to-peak value, the peak value, the effective value, the frequency, and the period of this voltage waveform. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following results. It looks like the source voltage on channel 1 has a peak-to-peak span of roughly 7.6 divisions. You note it's a little asymmetric and the positive half seems to be larger than the negative half, but not by much. Regardless, at 2 volts per division, this corresponds to a peak-to-peak value of roughly 15.2 volts. If we assume this waveform to be zero-centered, which it obviously isn't, a 15.2 volt peak-to-peak value corresponds to a peak value of 7.6 volts. A 7.6 volt peak value corresponds to an effective value of approximately 5.4 volts. The oscilloscope is displaying a frequency of 1500.7 Hz in the lower right-hand corner. If we wanted to confirm the accuracy of this automated measurement, one can manually measure the period. It looks like the two zero crossings going positive are separated by roughly 6.6, 6.7-ish divisions. Let's say 6.65 divisions. At the given horizontal sensitivity of 100 microseconds per division, this corresponds to a period of 665 microseconds. If we invert this measured period, we find this corresponds to a frequency of 1503.8 Hz, extremely close to the automatically displayed frequency of 1500.7 Hz. Let's just go with the automatically displayed value of 1500.7 Hz. This corresponds to a period of 666.4 microseconds. Given the above information, if we were to represent the source voltage displayed on channel 1 as a phasor equivalent, it would be equal to 5.4 volts at an angle of 0 degrees, assuming this is our reference. Now, let's display channel 2 on the oscilloscope using the same vertical sensitivity as channel 1 of 2 volts per division. Doing so rewards us with a fuzzy blue line that yields little usable data. What's wrong? Is there really no voltage drop across the sensing resistor? By all means, pause the lecture and think about this. What would you do to convince channel 2 to share some of its secrets? If you're tracking, you should have arrived at the following solution. There is a voltage drop across the sensing resistor, only it's extremely small in comparison to the voltage displayed on channel 1. Only when viewed at the same scale as channel 1 does channel 2 appear to be a flat, fuzzy line. We need to change the vertical sensitivity of channel 2 only. If channel 2 is viewed using a more appropriate vertical sensitivity of 10 millivolts per division, a sinusoidal waveform appears with some pretty measurable properties. Before diving into these details, answer me this simple question. Given the voltage on channel 2 is an indirect means of measuring and displaying current through the element in question, and the voltage waveform on channel 1 is the voltage across it, what type of element is this unknown element? Is it a resistor, a capacitor, or an inductor? You should be able to recall very memorable relations regarding voltage and current for these basic elements. By all means, pause the lecture and think about this. If you're tracking, you should have arrived at the following answer. Recall that current is in phase with the voltage across purely resistive elements. Current leads the voltage across purely capacitive elements by 90 degrees. And finally, current lags the voltage across purely inductive elements by 90 degrees. Given these facts and this observation, this unknown element is undoubtedly primarily inductive in nature, given channel 2, our indirect means of measuring and displaying current through the element in question, is clearly lagging channel 1, or more direct means of measuring and displaying voltage across the element in question. Is it lagging by exactly 90 degrees? I don't know. We'll have to measure it to be certain. This being said, current is clearly lagging voltage, and we're obviously dealing with a largely inductive element. That's the larger point of this technique. Let's now make some precise measurements of the voltage waveform displayed on channel 2. You'll note we're not using the automated transfer function utility for channel 2 for this exercise. It's still being displayed as voltage. See if you can determine the peak-to-peak value, the peak value, and the effective value of the voltage waveform on channel 2. Additionally, see if you can determine the relative phase shift between the two waveforms given the voltage waveform on channel 1 is assumed to be our reference. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following results. It looks like the voltage waveform on channel 2 has a peak-to-peak span of roughly 4.4 divisions. At a vertical sensitivity of 10 millivolts per division, this corresponds to a peak-to-peak value of roughly 44 millivolts. 44 millivolt peak-to-peak value would correspond to a peak value of 22 millivolts. A 22 millivolt peak value would correspond to an effective value of approximately 15.5 millivolts. It looks like the voltage waveform on channel 2 is lagging the waveform on channel 1 by, let's say, 1.5 divisions. Given the horizontal sensitivity is set to 100 microseconds per division, this corresponds to a backward shift of roughly 150 microseconds. Given this 1500 Hz waveform has a period of approximately 666.4 microseconds, a backward shift of 150 microseconds corresponds to a phase shift of roughly negative 81 degrees. It's not lagging by a perfect 90 degrees. However, we are clearly favoring the inductive end of the spectrum. Given the above information, if we were to represent the voltage across the sensing resistor displayed on channel 2 as a phasor equivalent, it would be equal to 15.5 millivolts at an angle of negative 81 degrees. Now, given channel 2 is in actuality the voltage drop across a 5 ohm sensing resistor, see if you can use Ohm's law to determine the current through it as a phasor equivalent. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following result. Ohm's law shows us that the current through the 5 ohm sensing resistor is a voltage phasor of 15.5 millivolts at an angle of negative 81 degrees over the complex impedance of 5 ohms at an angle of 0 degrees. The calculation yields a current of roughly 3.1 milliamperes at an angle of negative 81 degrees. If we wanted to, we could use this same scaling factor to derive other properties for the indirect means of measuring and displaying current. However, we got what we need. We know the phasor equivalent voltage across the unknown element and the phasor equivalent of current through it. Now, see if you can use Ohm's law to determine the impedance of the unknown element and the components, note the plural, components, that comprise this impedance. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following results. Impedance is equal to voltage over current. Substituting our given values, impedance appears to be approximately 1,727.3 ohms at an angle of 81 degrees, or roughly 1.7 kiloohms at an angle of 81 degrees, supporting our earlier hypothesis that this impedance is largely inductive. If this impedance was purely inductive, we'd be able to directly solve for the component level value of the inductor satisfying this condition. However, since it's only largely inductive in nature, this necessitates another intermediary step. We need to resolve this impedance represented as a magnitude and direction using polar format into real and reactive components using rectangular format. Doing so, we find 1,727.3 ohms at an angle of 81 degrees in polar format to be equivalent to 269.1 plus J 1706.2 using rectangular format. Given the real portion is the resistive element and the imaginary component is the reactive inductive portion, we need to determine the components that would satisfy this condition at the given frequency. A 269.1 ohm resistor would satisfy the real component condition. Solving for the element satisfying the imaginary component condition necessitates a bit more work. Given the imaginary component is clearly inductive, we can rearrange the inductive impedance formula to solve for inductance and substitute in our given magnitude and frequency values. Doing so yields an inductance value of roughly 180 millihenries. We can be certain that our unknown impedance is a 269.1 ohm resistor in series with a 180 millihenry inductor at 1,500 Hz. When we crack open the mystery box, we are astonished to find that this isn't exactly true, because the circuit in question actually contains only a 200 ohm resistor in series with a 180 millihenry inductor. What's the deal? Has Ohm's law been proven wrong? Far from the truth. Note that real-world components include small deviations from ideal behavior. Inductors, since they're composed of coils of wire, sometimes contain a measurable amount of internal resistance that can be modeled as a small internal resistance in series with the reactive portion. Most likely, this is a 180 millihenry inductor that happens to have an internal resistance component of approximately 69.1 ohms in series with a 180 millihenry inductive portion. Given the 200 ohm resistor is in series with the 180 millihenry inductor with a 69.1 ohm internal resistance, this makes it appear as if the whole impedance is equal to 1,727.3 ohms at an angle of 81 degrees using polar format, or 269.1 plus J 1706.2 using rectangular format. Problem solved, all thanks to the oscilloscope's ability to indirectly display current through an element relative to the voltage across it. If you wanted to, you could also make use of the oscilloscope's ability to automatically rescale voltage as current using an appropriate transfer function. Here's a screenshot of channel 2 making use of a 200 mA per volt transfer function appropriate for a 5 ohm sensing resistor. You note all our previous values we obtained are still accurate, only using this automated means we could skip the conversion of voltage to current using the sensing resistor resistance. Not all oscilloscopes have this ability, nor is it mandatory. However, it sure is convenient. Before we bring this lecture to a close, let's perform an objective review of that last example problem. While I did progressively lead you through the steps by your nose, note I never asked you to perform a calculation we haven't done so already. That's the point. We really only added one new technique to our repertoire, notably using a sensing resistor and an oscilloscope to indirectly measure current through an unknown element. Everything else necessitated your prior understanding of Ohm's law, phasor representation, complex impedance, and basic sinusoidal properties, techniques we've already discussed at some length. Be honest. Did you understand everything we discussed? At risk of repeating myself, if you struggled with any aspect of the above exercise, your issue may not necessarily be rooted in your misunderstanding of using an oscilloscope and sensing resistor to indirectly measure and display current per se, but rather in your inability to use Ohm's law, phasor representation, complex impedances, and basic sinusoidal properties to their full effect. If you lack confidence in these aforementioned skills, I again direct your attention to these previous lectures and ask that you bring yourself up to speed because we are moving on with or without you. Alright, that's about it for current measurement using an oscilloscope. In conclusion, this lecture examined the means of indirectly measuring and displaying current on an oscilloscope using a small sensing resistor in series with an element of interest. While this technique does induce a bit of error because of some assumptions and simplifications made, it does yield reasonably accurate results and, importantly, allows the current through an element to be displayed with reference to the voltage across it. As we've learned in previous lectures, relative phase shift between voltage and current is an extremely important property, and this simple technique allows a technician to experimentally obtain this data. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.